Right now, as you sit reading this, you exist in a universe that shouldn't be possible. Look around you. The temperature in your room is roughly the same everywhere. Give or take a few degrees. This seems perfectly normal until you realize that on cosmic scales, this kind of temperature uniformity should be absolutely impossible. Yet, when we look out into the deepest reaches of space and measure the ancient light from the universe's birth, we discover something that has left scientists baffled for over 50 years. The entire observable universe has essentially the same temperature everywhere down to 1 part in 100,000. Here's what makes this discovery so profoundly disturbing. Regions of space that are separated by billions of light years. Distances so vast that light from one region could never have reached the other, even if it had been traveling. Since the moment of the Big Bang, somehow maintain identical temperatures with precision that exceeds the finest scientific instruments ever built. We thought the early universe should be a chaotic, turbulent place filled with hot spots and cold regions scattered randomly across space. We were completely wrong about the universe's fundamental character. The numbers are staggering when you grasp their full implications. The cosmic microwave background radiation, the afterglow of the Big Bang that fills every cubic centimeter of space, shows temperature variations of only 0.0001 Kelvin across regions that span the entire observable universe. To put this precision in perspective, it's like discovering that every grain of sand on every beach on Earth has exactly the same temperature, measured to the nearest thousandth of a degree, despite these grains having no possible way to communicate or share energy with each other. Scientists from NASA's Cosmic Background Explorer mission announced in 1992 that they had measured this cosmic smoothness with unprecedented accuracy, confirming what seemed impossible. The universe exhibits a level of thermal equilibrium that violates everything we understand about causality, thermodynamics, and the fundamental limits of information transfer. Dr. John Mather, who won the Nobel Prize for this discovery, called it the most perfect blackbody spectrum ever observed in nature. So perfect that it challenges our basic understanding of how physical systems can achieve equilibrium. Tonight, we're going to explore the most profound mystery in modern cosmology. You're about to discover why the universe's smoothness represents a problem so fundamental that it questions our basic understanding of space, time, and causality itself. We'll journey from the cosmic microwave background that bathes the universe in ancient light to the theoretical frontiers where scientists propose that reality itself inflated faster than light during the universe's first fraction of a second. But first, consider this disturbing implication. If the universe achieved this impossible smoothness through natural processes, what does that reveal about the nature of space and time that we haven't yet grasped? And if the smoothness required something beyond known physics to explain, what profound truths about reality's fundamental structure are we missing? This isn't just about cosmology or theoretical physics. This is about discovering that the universe operates according to principles that seem to violate the most basic laws of cause and effect. What appears to be cosmic perfection reveals itself as cosmic impossibility. What looks like natural harmony becomes evidence that nature herself might operate according to rules we haven't even begun to understand. The ancient Greeks wondered whether the cosmos was ordered or chaotic. Modern science has discovered something far more mysterious. The cosmos is so perfectly ordered that this perfection itself becomes the deepest chaos, a challenge to everything we think we know about how reality can possibly work. By the time we finish this journey, you will understand why the universe's smoothness has forced scientists to propose that space itself can expand faster than light, that quantum fluctuations can become classical reality, and that the entire observable universe might be just one bubble in an infinite cosmic foam. You will discover why solving the smoothness problem has led to theories suggesting that most of reality remains forever hidden beyond our cosmic horizon. You will learn why astronomers now say that the universe we can observe, containing over 2 trillion galaxies spanning 93 billion light-years, represents less than a tiny fraction of what actually exists. And you will see why understanding cosmic smoothness reveals that the deepest questions about existence are unanswered by what we can see, but by contemplating the infinite reality that must remain forever invisible. The smoothness we observe in the cosmic microwave background isn't just a measurement. It is evidence that reality itself operates according to principles that transcend our everyday understanding of space, time, and causality. Tonight, you are going to discover that the most familiar aspect of our universe, its apparent uniformity and order, is actually its most mysterious and impossible characteristic. Subscribe and hit the thumbs up button if you're ready to have your understanding of cosmic order completely transformed. And here is a question that will haunt your thinking. If the universe achieved impossible smoothness through unknown physics, what other impossible phenomena might be hiding in plain sight around us? Comment your most mind-bending thoughts below. I'll pin the answer that best captures the cosmic mystery we're about to explore. The universe that appears most normal and orderly to our daily experience turns out to be the most extraordinary and mysterious cosmic phenomenon ever discovered. We're about to find out why the smoothness that makes life possible shouldn't exist at all, and why solving this puzzle has led scientists to the edges of human understanding itself. The ancient question of cosmic order versus cosmic chaos finds its resolution in the recognition that perfect cosmic order is so improbable that it becomes indistinguishable from perfect cosmic mystery. Now let's begin our journey into the heart of this impossible smoothness. Chapter 1. Perfect Temperature. The discovery that shattered our understanding of cosmic evolution began with the most mundane observation imaginable: taking the universe's temperature. In 1965, Arno Penzias and Robert Wilson were trying to eliminate mysterious static from their radio antenna at Bell Labs when they stumbled upon the most important cosmological discovery of the 20th century. What they thought was interference from pigeon droppings turned out to be the ancient echo of creation itself. Radiation from the Big Bang that has been cooling and redshifting for 13.8 billion years. But this discovery immediately created a problem that has haunted cosmology ever since. When Penzias and Wilson measured the temperature of this cosmic microwave background radiation, they found it to be remarkably uniform in every direction they looked. No matter where they pointed their antenna, north, south, toward the galactic center, away from it, the temperature remained constant at approximately 2.7 Kelvin above absolute zero, with variations so tiny they were initially undetectable. This uniformity seemed natural at first glance, like the comfortable assumption that room temperature should be roughly the same throughout your house. But cosmic scales are not house scales, and the implications of cosmic temperature uniformity became apparent only when physicists began calculating how thermal equilibrium actually works across vast distances and cosmic timescales. For any system to achieve uniform temperature, its components must be able to exchange energy until they reach thermal equilibrium. This requires what physicists call causal contact, the ability for energy and information to travel between different regions of the system. In your house, air circulation and heat conduction allow energy to flow from warmer areas to cooler areas until temperature equalizes. But the universe presents a problem of scale so extreme that such equalization should be fundamentally impossible. The cosmic microwave background we observe today originated approximately 380,000 years after the Big Bang, when the universe cooled enough for electrons and protons to combine into neutral hydrogen atoms. Before this moment, called recombination, the universe was opaque to light, like the interior of a star. After recombination, the universe became transparent, releasing the first light that could travel freely through space. the cosmic microwave background that Penzias and Wilson detected billions of years later. Here's where the impossible precision reveals itself. When we mapped the cosmic microwave background across the entire sky using satellites like the Cosmic Background Explorer, COBE, and the Wilkinson Microwave Anisotropy Probe, WMAP, we find that regions separated by more than 2 degrees on the sky, representing vast cosmic distances, maintain identical temperatures to within 0.01% accuracy. These regions are separated by distances so enormous that light traveling at the cosmic speed limit could not have crossed between them even in the 380,000 years available before recombination. Dr. Alan Guth from MIT, who developed inflation theory to address this puzzle, explains the problem with a striking analogy. Imagine you have 2 people on opposite sides of a large mountain, each holding a thermometer. They can't see each other, can't communicate, and have never met. Yet somehow their thermometers read exactly the same temperature to incredible precision. This is essentially what we observe in the cosmic microwave background. The mathematical precision of this temperature uniformity becomes even more remarkable when you consider the cosmic scales involved. Light travels approximately 300,000 kilometers per second. But the observable universe spans about 93 billion light-years in diameter. During the 380,000 years between the Big Bang and recombination, light could have traveled at most 380,000 light-years, less than 0.0004% of the current observable universe's diameter. This means that when we observe the cosmic microwave background, we were seeing regions that were never in causal contact with each other during the universe's early history. They had no mechanism for exchanging energy or information, no way to know what temperature they should maintain relative to distant regions. Yet somehow they achieved thermal equilibrium with precision that surpasses any natural thermal system ever studied in laboratory physics. NASA's Planck satellite, launched in 2009, measured this temperature uniformity with unprecedented precision and confirmed that the cosmic microwave background represents the most perfect black-body spectrum ever observed in nature. A black-body spectrum emerges when a system reaches perfect thermal equilibrium, where energy is distributed optimally across all possible frequencies according to precise statistical mechanics. Achieving such perfection requires extensive energy exchange and mixing, exactly what should have been impossible in the early universe as causally disconnected regions. The temperature measurements reveal additional layers of mystery when examined in detail. Not only is the cosmic microwave background uniformly smooth on large scales, but the tiny temperature fluctuations that do exist, about 1 part in 100,000, follow statistical patterns that appear fine-tuned for galaxy formation. These fluctuations provide the gravitational seeds that eventually grew into the cosmic web of galaxies and galaxy clusters we observe today. But here's what makes the smoothness problem even more profound. If the universe achieves such perfect thermal equilibrium naturally through known physics, it would have required energy exchange across distances and timescales that exceed what general relativity allows. The cosmic microwave background represents physical evidence that the early universe somehow violated the fundamental speed limit of information transfer that governs all other physical processes. To put this violation in perspective, consider that Einstein's theory of relativity establishes that nothing, no matter energy or information, can travel faster than light in vacuum. This speed limit isn't just a practical constraint. It's fundamental to the structure of space-time itself. Yet the cosmic microwave background implies that somehow information about temperature and energy density was shared across cosmic distances in times much shorter than light travel time would allow. Traditional cosmology, based on the standard Big Bang model without additional mechanisms, predicts that the cosmic microwave background should show dramatic temperature variations across the sky, hot spots, and cold regions scattered randomly like a cosmic patchwork quilt. Instead, we observe smoothness so perfect that it seems to require physics beyond the standard model of cosmology. The precision of this cosmic temperature goes beyond anything achieved in terrestrial physics laboratories. The most carefully controlled thermal systems on Earth, specialized blackbody cavities used for calibrating infrared sensors, achieve temperature uniformity measured in parts per thousand. The cosmic microwave background achieves uniformity measured in parts per 100,000 across a system containing more mass energy than trillions of galaxies. Consider what this means for our understanding of cosmic evolution. The universe we observe today, with its intricate structure of galaxies, stars, and planets, emerged from initial conditions so smooth and uniform that they seem almost artificially prepared. This smoothness provided the stable foundation upon which all subsequent cosmic complexity could develop. Yet achieving such smoothness through natural processes appears to require violations of fundamental physical principles. Now we're going to explore how this perfect temperature reveals an even deeper mystery. The universe exhibits not just thermal uniformity, but geometric flatness and causal coordination that compound the smoothness problem into what cosmologists call the horizon problem, the discovery that our entire observable universe appears to be just one small causally connected patch of a vastly larger cosmic reality. Chapter 2: Horizon Problem. The cosmic smoothness mystery deepens dramatically when you realize that the uniform temperature of the cosmic microwave background represents only the most obvious manifestation of a far more fundamental problem. The entire observable universe appears to have emerged from initial conditions that required causal coordination across distances that vastly exceed what physics allows. This is the horizon problem, and it suggests that everything we can see represents just one tiny, specially prepared region within an unimaginably larger cosmic reality. To understand the horizon problem, imagine you're standing in the center of a vast, dark plane at night holding a flashlight. The circle of light around you represents your horizon, the boundary of what you can observe given the limited range of your light. In cosmology, the cosmic horizon represents the boundary of what we can observe given the finite speed of light and the finite age of the universe. Light from regions beyond our cosmic horizon has not had enough time to reach us since the Big Bang, making those regions permanently invisible, regardless of how powerful our telescopes become. Dr. Robert Dick from Princeton University first articulated the horizon problem in 1968, pointing out that the cosmic microwave background appears uniform across angular separations that correspond to regions far beyond each other as cosmic horizons during the early universe. When we observe cosmic microwave background radiation coming from opposite directions in the sky, we're seeing light from regions that were separated by distances much larger than light could have traveled during the time available for causal interaction. The mathematical reality of cosmic horizons becomes clear when you calculate the maximum distance light could have traveled during specific epochs of cosmic history. At the moment of recombination, when the cosmic microwave background was released, the universe was approximately 380,000 years old. Light traveling at 300,000 kilometers per second for 380,000 years could have covered at most 380,000 light years. But the regions of space from which we receive cosmic microwave background radiation today were separated by distances exceeding 90 million light years at that time. This means that approximately 99% of the observable cosmic microwave background comes from regions that were never in causal contact with each other during the universe's early history. They had no mechanism for coordinating their temperatures, densities, or expansion rates. Yet somehow they achieved identical physical conditions with extraordinary precision. It is as if you discovered that every grain of sand on every beach on Earth was not only the same temperature, but also the same size, composition, and crystalline structure, despite these grains having no possible way to coordinate their properties. The European Space Agency's Planck satellite has mapped the cosmic microwave background with unprecedented resolution, revealing that this causal coordination extends to the finest observable scales. Temperature fluctuations that span less than 1 degree on the sky, representing regions that were definitely within each other as horizons, show the same statistical properties as fluctuations. Spanning 180 degrees, representing regions that were completely beyond each other as causal reach. But the horizon problem extends far beyond temperature uniformity to encompass what cosmologists call the flatness problem. Measurements of cosmic geometry using type Ia supernovas as standard candles reveal that space is flat to within observational uncertainty. This geometric flatness means that the universe as total energy density sits precisely at the critical value that separates eternal expansion from eventual gravitational collapse. The flatness precision required to achieve today's geometric observations is almost incomprehensibly fine-tuned. Dr. Alan Guth's calculations show that the early universe's energy density must have been within 1 part in 1060 of the critical density to produce the flatness we observe today. To appreciate this precision, consider that 1060 is approximately the number of atoms in the entire observable universe. The universe's initial conditions were fine-tuned to a precision equivalent to hitting a target the size of a single atom from a distance spanning the entire cosmos. This geometric fine-tuning compounds the horizon problem because achieving such precision requires coordination, not just of temperature and density, but of space-time curvature itself across causally disconnected regions. Different regions of the early universe somehow knew to maintain identical expansion rates and energy densities, despite having no mechanism for sharing information about their local physical conditions. NASA's Cosmic Background Explorer revealed another dimension of the horizon problem through precise measurements of cosmic isotropy, the universe's identical appearance in all directions. When we observe the cosmic microwave background, galaxy distributions, and large-scale structure, we find statistical uniformity regardless of which direction we look. This isotropy implies that our local region of space is not special or preferred, yet achieving such uniformity across the entire observable universe requires causal coordination on impossible scales. The horizon problem becomes even more mysterious when you consider the universe's chemical uniformity. Observations of distant galaxies using the Hubble Space Telescope reveal that the ratio of light elements, hydrogen, helium, and lithium remains constant throughout the observable universe. These ratios were established during Big Bang nucleosynthesis, approximately 3 minutes after the initial expansion began, when different regions of space were even more causally disconnected than during recombination. Dr. Steven Winberg's calculations of primordial nucleosynthesis show that producing the observed chemical uniformity requires temperature and density coordination across regions that were separated by distances exceeding what light could traverse by factors of millions. Different regions of the early universe somehow maintained identical nuclear reaction conditions, despite having no causal mechanism for coordination. The large-scale structure surveys conducted by the Sloan Digital Sky Survey reveal that the horizon problem extends to the distribution of galaxies and dark matter across cosmic time. The cosmic web, the largest scale structure in the universe, shows statistical homogeneity across distances that span the entire observable cosmos. Galaxy clusters, superclusters, and voids are distributed with uniform statistical properties regardless of location or direction, implying coordination across scales that vastly exceed causal horizons throughout cosmic history. But perhaps the most profound aspect of the horizon problem is its implication for cosmic initial conditions. Standard Big Bang cosmology requires that the universe began in a state of extraordinary special preparation, uniform density, flat geometry, and synchronized expansion across regions that had no causal mechanism for achieving such coordination. This suggests either miraculous fine-tuning of initial conditions or the operation of physical processes beyond our current understanding. The horizon problem also raises fundamental questions about cosmic uniqueness versus cosmic multiplicity. If the observable universe represents one causally connected region that achieves special initial conditions, what exists beyond our cosmic horizon? Are there other regions with different physical conditions, different constants of nature, or entirely different evolutionary histories? Consider the philosophical implications of the horizon problem. Everything you have ever seen, every star in the night sky, every galaxy observed by the most powerful telescopes, every particle of matter and energy that has ever influenced Earth's evolution, all of this represents less than one tiny patch within a cosmic reality that extends far beyond what we can ever observe. The horizon problem suggests that the universe we can study scientifically is just one small sample of cosmic conditions that may be completely unrepresentative of the larger reality in which we re-embedded. The horizon problem doesn't just challenge our understanding of cosmic evolution. It challenges our understanding of what constitutes scientific evidence and cosmic knowledge. If the universe we observe represents only a tiny, specially prepared region within an unimaginably larger cosmos, how can we ever hope to understand the true nature of cosmic reality? Now we're going to explore how scientists have attempted to solve the horizon problem through one of the most ambitious theoretical proposals in the history of physics: cosmic inflation. The idea that space itself expanded faster than light during the universe's first fraction of a second, creating the impossible coordination we observe today. Chapter 3. Inflation Theory. In 1980, a young physicist at MIT named Alan Guth proposed what seemed like an impossible solution to the horizon problem. Perhaps space itself expanded faster than the speed of light during the universe's first tiny fraction of a second, stretching what was once a small causally connected region into the vast smooth cosmos we observe today. This proposal, called cosmic inflation, represents one of the most audacious theoretical leaps in the history of science, suggesting that the fundamental structure of space-time itself can violate what we thought were absolute speed limits. The core insight behind inflation theory emerges from a subtle distinction in Einstein's theory of relativity. While nothing can travel through space faster than light, space itself is under no such constraint. The fabric of space-time can expand, contract, or deform at any rate allowed by the equations of general relativity. During cosmic inflation, space expanded exponentially, carrying matter and energy along with it while preserving the causal relationships established during the brief period when the entire observable universe existed within a single horizon. Dr. Guth's original inflation model proposed that the universe underwent exponential expansion during the first 10 to 36 to y-32 seconds after the Big Bang, a time interval so brief that light could travel only a distance smaller than a proton. During this inflationary epoch, space expanded by a factor of at least 1026, stretching a region initially smaller than a subatomic particle into a volume larger than a basketball. This expansion rate means that space grew faster than light could traverse it, explaining how causally connected initial conditions could produce the smooth universe we observe across our entire cosmic horizon. The mathematics of exponential expansion reveal why inflation solves the horizon problem so elegantly. Imagine marking 2 points on a deflated balloon, then inflating the balloon rapidly. As the rubber stretches, the marked points move apart faster than any signal could travel across the balloon's surface. Yet they maintain identical properties because they originated from the same small region where coordination was possible. Cosmic inflation worked similarly. taking a tiny region of space where thermal equilibrium and causal coordination were naturally achievable and stretching it to encompass our observable universe. But inflation theory required proposing a new type of energy field, the inflation field, that could drive exponential expansion through its peculiar physical properties. Unlike ordinary matter and radiation, which become less dense as space expands, the inflation field maintained constant energy density during expansion, providing the repulsive gravitational pressure necessary to accelerate cosmic growth. This field would need to dominate the universe's energy budget completely during the inflationary epoch, then decay rapidly into ordinary matter and radiation to produce the hot, dense state required for standard Big Bang nucleosynthesis. Dr. Andre Lind from Stanford University developed a theoretical framework for inflation field dynamics, showing how quantum field theory allows energy fields to temporarily violate normal gravitational attraction. During inflation, the universe existed in a false vacuum state, a temporary condition where quantum fields maintained enormous energy density while exhibiting repulsive gravitational effects. This false vacuum drove exponential expansion until quantum fluctuations triggered the field's decay into the true vacuum state we observe today. The inflationary transition from false vacuum to true vacuum released the enormous energy that heated the universe to the extreme temperatures required for Big Bang cosmology. This process, called reheating, converted the inflation field's energy into the particles and radiation that filled the early universe, establishing the initial conditions for subsequent cosmic evolution. The energy released during reheating exceeded the total mass energy of the observable universe today, demonstrating the incredible energy scales involved in cosmic inflation. NASA's cosmic background Explorer and subsequent missions have found remarkable evidence supporting inflation theory through precise measurements of cosmic microwave background fluctuations. Inflation theory predicts that quantum mechanical uncertainty in the inflation field should have produced tiny density fluctuations that were stretched to cosmic scales during exponential expansion. These fluctuations should appear as temperature variations in the cosmic microwave background, with specific statistical properties that distinguish inflation from other theoretical proposals. The observed cosmic microwave background fluctuations match inflation theory's predictions with extraordinary accuracy. The temperature variations show a nearly scale-invariant spectrum, meaning fluctuations have similar amplitudes across a wide range of angular scales, exactly as predicted by inflation models. The fluctuations also exhibit Gaussian statistics and specific correlations that arise naturally from quantum field fluctuations, but would be difficult to explain through other mechanisms. Dr. Alexei Starobinsky's analysis of inflation field dynamics revealed that different inflation models make distinct predictions about cosmic microwave background polarization patterns. The European Space Agency's Planck satellite has measured these polarization signatures, providing additional tests of inflation theory that probe the quantum mechanical processes occurring during the universe's first fraction of a second. But inflation theory raises profound questions about the nature of space, time, and cosmic uniqueness. If inflation can occur once, it can presumably occur repeatedly, creating what cosmologists call eternal inflation. In this scenario, new inflationary regions continuously emerge within the larger cosmic landscape, each producing separate pocket universes with potentially different physical laws and constants of nature. Our observable universe would represent just one bubble in infinite cosmic foam of inflating regions. The eternal inflation scenario suggests that cosmic inflation may be an ongoing process occurring throughout an infinite cosmic landscape. While inflation ended in our local region 13.8 billion years ago, it may continue elsewhere, producing new universes with different vacuum states, different particle physics, and different values for fundamental constants. This infinite cosmic reproduction makes our universe's apparent fine-tuning less mysterious. We exist in a region with properties compatible with complexity and life, because regions with incompatible properties would not produce observers. Dr. Alan Lynn's chaotic inflation models demonstrate that inflation may be generic rather than special, arising naturally from quantum fluctuations in energy fields rather than requiring carefully prepared initial conditions. If chaotic inflation is correct, then inflationary universe creation represents a fundamental feature of cosmic evolution rather than a special event that occurred once in our cosmic history. The energy scales required for cosmic inflation approach the Planck scale, the regime where quantum mechanics and general relativity meet, and where our current understanding of physics breaks down completely. Inflation theory necessarily involves physics beyond the standard model, requiring new particles, new energy fields, and possibly new dimensions of space and time that remain hidden at lower energy scales accessible to current experiments. Consider what inflation theory implies about the nature of reality itself. If our entire observable universe emerged from quantum fluctuations in a microscopic region of space, then the cosmos we can study scientifically represents just one possible realization of quantum mechanical uncertainty. The galaxies, stars, and planets we observe are specific outcomes of quantum processes that could have produced completely different cosmic structures with equal probability. Inflation theory also suggests that space-time itself is far more flexible and dynamic than our everyday experience suggests. The space that contains all cosmic structure, all matter and energy, all the history of cosmic evolution, this space can expand, stretch, and deform according to quantum field dynamics operating on timescales and energy scales that dwarf human experience. But perhaps the most profound implication of inflation theory is that it makes cosmic smoothness not just possible, but inevitable. Rather than requiring miraculous fine-tuning or special initial conditions, the smooth universe we observe emerges naturally from quantum field dynamics operating during the universe's earliest moments. The horizon problem dissolves because the entire observable universe originated within a single causal horizon that was subsequently stretched to cosmic scales through exponential expansion. Now we're going to explore how inflation theory led to an even more startling discovery. The cosmic microwave background reveals not just smoothness, but specific patterns of tiny fluctuations that appear to preserve quantum mechanical uncertainty on cosmic scales, suggesting that classical reality itself emerged from quantum mechanical processes during the universe's first fraction of a second. Chapter 4. Quantum Seeds. The most mind-bending discovery in modern cosmology isn't just that the universe is smooth. It is that embedded within this cosmic smoothness are tiny fluctuations that appear to be the fossilized remains of quantum mechanical uncertainty stretched to galactic scales. When scientists mapped the cosmic microwave background with unprecedented precision, they found that the universe's birth preserved quantum mechanical processes and patterns that now span billions of light years, suggesting that the classical reality we observe emerged directly from quantum fluctuations during cosmic inflation. The story of quantum seeds begins with Werner Heisenberg's uncertainty principle, which reveals that quantum systems cannot have perfectly definite properties. Even in complete vacuum, quantum fields fluctuate randomly due to fundamental uncertainty in their energy and momentum. These vacuum fluctuations create virtual particles that briefly appear and disappear on timescales so short they normally have no observable consequences in our macroscopic world. But during cosmic inflation, these microscopic quantum fluctuations were stretched and amplified into macroscopic density variations that became the seeds for all cosmic structure. Dr. Vyacheslav Mukhanov and Dr. Alexei Starobinsky first calculated how quantum fluctuations in the inflation field could produce observable cosmic structure during the early 1980s. Their analysis revealed that as space expanded exponentially during inflation, Quantum uncertainty in the inflation field would create random variations in energy density across different regions of space. These variations started smaller than atomic nuclei, but were stretched to astronomical scales as cosmic inflation proceeded. The quantum to classical transition that occurred during inflation represents one of the most dramatic examples of quantum decoherence ever identified in nature. Quantum fluctuations that initially existed in superposition states, simultaneously fluctuating up and down according to quantum mechanical probability, became frozen into classical density variations as they were stretched beyond the cosmic horizon. The act of inflationary expansion itself caused quantum uncertainty to collapse into definite classical outcomes that persist in cosmic structure today. NASA's Wilkinson Microwave Anisotropy Probe, WMAP, revealed the quantum fingerprints of this process through detailed measurements of cosmic microwave background temperature fluctuations. The observed fluctuations display statistical properties that match quantum mechanical predictions with extraordinary precision. The fluctuations are nearly Gaussian distributed, following the bell curve statistics expected from quantum vacuum fluctuations, and exhibit correlations across different angular scales that preserve quantum coherence information from the inflationary epoch. The European Space Agency's Planck satellite extended these measurements to reveal even subtler quantum signatures in the cosmic microwave background. Planck detected tiny deviations from perfect Gaussianity in scale invariance that provide direct windows into the quantum field dynamics occurring during inflation. These non-Gaussian signatures encode information about the specific shape of the inflation field's energy potential and the interactions between quantum fluctuations during exponential expansion. But here is where the quantum seed story becomes truly remarkable. The cosmic microwave background fluctuations we observe today represent a complete fossil record of quantum mechanical processes occurring during the universe's first 10 to 32 seconds. Every hot spot and cold spot in the cosmic microwave background corresponds to a specific quantum fluctuation that occurred in a microscopic region of the inflation field before being stretched to cosmic proportions. We are literally observing quantum mechanics operating on the scale of the entire observable universe. The amplitude of cosmic microwave background fluctuations provides direct measurement of quantum vacuum energy during inflation. The temperature variations we observe, approximately 100,000, directly reflect the strength of quantum fluctuations in the inflation field at the moment they crossed outside the cosmic horizon and became classical. This makes the cosmic microwave background the most precise measurement of quantum field theory predictions ever achieved in any physical system. Dr. Juan Maldesena's theoretical work on inflation and quantum field theory revealed that different inflation models predict distinct quantum signatures that should be observable in cosmic microwave background polarization patterns. The simplest inflation models predict tensor perturbations, gravitational waves produced by quantum fluctuations in space-time geometry itself during inflation. These primordial gravitational waves would create specific polarization patterns in the cosmic microwave background that encode direct information about quantum gravity effects during the universe's birth. The search for these tensor perturbations represents one of the most ambitious experimental programs in modern physics. Ground-based telescopes like BICEP and balloon-borne experiments like Boomerang have searched for the characteristic B-mode polarization patterns that would signal primordial gravitational waves. While definitive detection remains elusive due to interference from galactic dust, the ongoing search probes energy scales approaching the Planck energy, where quantum mechanics and general relativity unite. The quantum seed story reveals something profound about the nature of reality itself. The classical world we observe emerged from quantum mechanical processes through cosmic inflation acting as a natural quantum amplifier. The galaxies, stars, and planets that make up today's cosmic structure all trace their origins to specific quantum fluctuations that occurred in regions smaller than elementary particles during the universe's first moments. To grasp the magnitude of this quantum to classical amplification, consider that a typical quantum fluctuation during inflation started with an amplitude smaller than 10 to 50 meters, far smaller than any subatomic particle, and was amplified to cosmic scales exceeding billions of light-years. This represents an amplification factor of approximately 1080, making cosmic inflation the most powerful natural amplifier ever identified in physics. The large-scale structure surveys conducted by projects like the Sloan Digital Sky Survey have confirmed that the quantum seeds preserved in the cosmic microwave background indeed grew into the cosmic web of galaxies and galaxy clusters through gravitational amplification over billions of years. The statistical properties of galaxy distributions match predictions based on cosmic microwave background fluctuations with remarkable precision, confirming that quantum fluctuations during inflation provided the gravitational seeds for all subsequent cosmic structure formation. But the quantum seed story raises profound questions about the nature of cosmic uniqueness and quantum measurement. If our universe represents one specific realization of quantum mechanical uncertainty during inflation, then alternative cosmic structures with different galaxy distributions, different stellar populations, and different evolutionary histories were equally probable quantum outcomes. We observe one particular universe not because it was predetermined, but because quantum measurement during inflation selected one specific outcome from an infinite ensemble of quantum possibilities. Dr. David Deutsch's work on quantum mechanics and the multiverse suggests that inflation may have produced not just one universe, but all possible quantum outcomes simultaneously in parallel branches of cosmic reality. From this perspective, the cosmic microwave background we observe represents just one quantum measurement outcome, while other cosmic microwave background patterns exist in parallel universes corresponding to different quantum measurement results during inflation. The quantum seeds preserved in cosmic structure also provide a unique laboratory for testing quantum field theory predictions under conditions impossible to reproduce in terrestrial laboratories. The energy scales, field strengths, and space-time curvatures involved in cosmic inflation vastly exceed anything achievable through human technology, making cosmological observations essential for probing fundamental physics beyond the standard model. Consider what the quantum seeds reveal about your own cosmic origins. Every atom in your body formed inside stars, whose birth was triggered by gravitational collapse in regions where quantum fluctuations during inflation created slight overdensities. The calcium in your bones, the iron in your blood, the oxygen you breathe, all exist because specific quantum measurement outcomes during the universe's first fraction of a second produce the gravitational seeds necessary for star formation in our cosmic neighborhood. The quantum seed story transforms how we understand the relationship between quantum mechanics and classical reality. Rather than representing separate domains of physics that somehow interact mysteriously, quantum mechanics and classical reality reveal themselves as different aspects of cosmic evolution. Classical reality doesn't exist independently of quantum mechanics. It emerged from quantum mechanics through the natural amplification process of cosmic inflation. Now, we're going to explore how these quantum seeds grew into the vast cosmic web that spans the observable universe today, and why understanding this growth process reveals that the smooth universe we initially observed actually conceals the most complex and beautiful structures ever discovered in nature. Chapter 5. Hidden Structure. The cosmic smoothness that initially puzzled scientists conceals within it the most intricate and beautiful architectural patterns ever discovered. A vast cosmic web spanning billions of light years that reveals How quantum fluctuations from the universe's birth grew into the largest structures in existence. What appeared to be uniform cosmic emptiness actually teems with invisible scaffolding that guides galaxy formation, controls stellar evolution, and shapes the destiny of every cosmic structure we observe today. The hidden structure story begins with the recognition that the cosmic microwave background's tiny temperature fluctuations, those 1 part in 100,000 variations that seemed almost negligible, actually encoded a complete blueprint for cosmic architecture. Each fluctuation represented a region where matter density was slightly higher or lower than the cosmic average, creating gravitational seeds that would grow over billions of years through the relentless pull of gravity acting on dark matter and ordinary matter alike. Dr. Yakov Zeldovich from the Soviet Union first calculated how these primordial density fluctuations would evolve under gravitational attraction during the 1970s. His analysis revealed that tiny overdensities would grow exponentially over time, pulling in surrounding matter while creating increasingly pronounced density contrasts. Meanwhile, underdense regions would become more underdense as matter flowed out toward the growing concentrations, creating a cosmic pattern of dense filaments separated by vast empty voids. The mathematics of gravitational growth shows that initially small density fluctuations become dramatically amplified as cosmic evolution proceeds. A region that started only 0.00% denser than average would grow to become 1% denser after a few 100 million years, then 10% denser after a billion years, eventually becoming dense enough to trigger gravitational collapse and star formation. This exponential amplification process transforms almost imperceptible quantum seeds into galaxy mass concentrations over cosmic time. But the hidden structure extends far beyond individual galaxies to encompass what cosmologists call the cosmic web, a vast network of dark matter filaments that spans the entire observable universe. Computer simulations like the Millennium Simulation and the Illustristing Project have revealed that dark matter organizes itself into a web-like pattern with dense nodes connected by thin filaments, separated by enormous empty regions called cosmic voids. The Sloan Digital Sky Survey, which mapped the three-dimensional positions of over 1 million galaxies, confirmed that this cosmic web predicted by simulations actually exists in nature. Galaxies are not randomly distributed throughout space, but instead trace out filamentary structures that span hundreds of millions of light-years. Galaxy clusters sit at the intersections of cosmic web filaments, while galaxies flow along the filaments like cities connected by cosmic highways. NASA's Hubble Space Telescope has captured images of this hidden structure through gravitational lensing observations that reveal dark matter distributions invisible to direct observation. When light from distant galaxies passes through massive dark matter concentrations, the gravity bends the light paths and distorts the background galaxy images. By analyzing these distortions, astronomers can map the dark matter scaffolding that underlies all visible cosmic structure. The cosmic web's architecture reveals elegant mathematical patterns that reflect the quantum mechanical origin of cosmic structure. The statistical properties of filament lengths, void sizes, and node separations all follow power law distributions that preserve information about the primordial fluctuation spectrum established during inflation. The cosmic web serves as a vast fossil record of quantum mechanical processes operating during the universe as first fraction of a second. Dr. Carlos Frank's simulations of cosmic structure formation demonstrate that the cosmic web develops through a process called hierarchical clustering, where small structures merge to form larger structures over cosmic time. Dark matter halos containing individual galaxies merge to form galaxy groups, which merge to form galaxy clusters, which merge to form superclusters in a cosmic evolutionary tree that spans from quantum fluctuations to the largest observable structures. But the hidden structure story reveals that cosmic voids, The vast empty regions between cosmic web filaments are not truly empty, but contain their own subtle architecture. Observations from surveys like the Dark Energy Survey show that cosmic voids contain sparse networks of smaller galaxies and dark matter substructures that trace out delicate patterns invisible to earlier surveys. Even cosmic emptiness has structure when examined with sufficient sensitivity. The cosmic web also exhibits unexpected symmetries and patterns that reflect underlying physical principles. The largest cosmic structures show statistical isotropy. They appear similar when viewed from any direction. Yet they also display hierarchical organization where larger structures are built from smaller structures in fractal-like patterns that repeat across multiple scales from galactic to cosmic. The hidden structure extends to time as well as space through what astronomers call cosmic evolution. Because light has finite speed, observing distant galaxies allows us to see cosmic structure as they existed billions of years ago. The Hubble Space Telescope's deep-field observations reveal that early cosmic structure was more chaotic and irregular than today's organized cosmic web, showing how gravitational evolution gradually imposed order on initially random quantum fluctuations. The James Webb Space Telescope is now observing cosmic structure formation during the universe's first billion years, revealing how the first galaxies formed within dark matter halos and began the process of converting primordial gas clouds into stars and heavy elements. These observations show that cosmic structure formation was well underway when the universe was only 5% of its current age, demonstrating how efficiently gravity can organize quantum seeds into complex cosmic architecture. But perhaps the most remarkable aspect of hidden cosmic structure is how it appears fine-tuned for complexity and life. The cosmic web creates environments where galaxies can form and evolve over billions of years while maintaining access to fresh gas supplies for continued star formation. The filamentary structure channels matter flow in ways that prevent galaxies from either becoming isolated or experiencing destructive collisions too frequently. The density contrast between cosmic web filaments and cosmic voids also appears optimized for producing the chemical elements necessary for rocky planets and biological life. In regions that are too dense, galaxies merge frequently and experience intense radiation that sterilizes potential planetary systems. In regions that are too sparse, galaxies lack the gravitational interactions necessary for triggering episodes of star formation that produce heavy elements. Dr. Max Tegmark's analysis of cosmic structure statistics reveals that the observed cosmic web exists in a narrow parameter range that maximizes both structural complexity and long-term stability. Slightly different initial conditions would have produced cosmic webs that either collapse too rapidly or remain too diffuse to support galaxy formation. The hidden structure we observe appears to represent an optimal solution to the challenge of building complexity in an expanding universe. Consider what the hidden structure reveals about your cosmic context. Earth orbits the Sun within the Milky Way galaxy, which sits on a minor filament of the cosmic web in a region called the local supercluster. This cosmic address determines the gravitational environment that has influenced our galaxy's evolution for billions of years, affecting the availability of gas for star formation, the frequency of galaxy interactions, and the overall stability of our cosmic neighborhood. The cosmic web's hidden structure also guides cosmic evolution into the far future. Computer simulations of cosmic evolution show that the cosmic web will continue organizing cosmic structure for hundreds of billions of years, although the pattern will gradually change as cosmic expansion accelerates and dark energy dominates over gravitational attraction. Eventually, cosmic web filaments will stretch and dissipate, leaving isolated galaxy clusters surrounded by ever-expanding voids. The hidden structure story transforms our understanding of cosmic architecture from random distribution to elegant organization. What initially appeared to be cosmic chaos reveals itself as cosmic cosmos, a universe where quantum mechanical uncertainty has been transformed through gravitational evolution into beautiful, complex, and functionally sophisticated architectural patterns that span the largest observable scales. Now, we're going to explore how this hidden cosmic structure enabled the formation of the first stars and galaxies, and why understanding cosmic dawn reveals that the smooth early universe contained all the information necessary to build the complex cosmic ecosystems that make planets' chemistry and life possible across cosmic time.